Hello, my name is Kent Ben Every. I'm a materials engineer here at Progressive Surface, and today I will be discussing the coating development work in thermal spray applications for semiconductor industry. During semiconductor manufacturing, wafers may undergo a plasma etching process. This process exposes the metal walls of the etch chamber to both erosion and corrosion. Applying a ceramic coating to the metal walls can reduce both the erosive and corrosive attacks of the chamber. One common method for applying a ceramic coating to a metal surface is thermal spraying. In thermal spraying, a powder is injected into the heated plume produced by a torch. Drag forces from the plume accelerate the powder particles while simultaneously heating them. The heated powder particles then impact on the substrate being coated and flatten into shapes called splats or lamellae. These splats adhere by contracting around the roughness of the underlying surface as they cool. For the semiconductor etch chamber application, the erosion and corrosion resistance of the coating increases with decreasing surface roughness and decreasing coating porosity. Thus, a goal of the semiconductor manufacturer is to identify the thermal spray technique that best produces a smooth, dense ceramic coating. A variety of thermal spray processes exist, and they produce plumes with different temperature and speed ranges, as you can see in the graph here. To deposit a ceramic coating, the powder particles need to be nearly fully molten before they impact the substrate. Testing has shown that the ceramic yttrium oxide can produce good protection in the etch chamber application. Yttrium oxide melts around 2,500 degrees centigrade. And as you can see, if we plot that temperature on our graph, that eliminates thermal spray techniques that produce plume temperatures below these values, such as flame spraying, HVAF, which is high velocity air fuel spraying, or cold spraying. Ensuring the yttrium oxide particles are fully molten will promote the spreading of the droplets during impact, helping to create the desired smooth, dense coating. Additionally, increasing the speed at which the droplets impact the substrate will also promote droplet spreading and help to create a smooth, dense coating. One means to increase the speed of the depositing droplets is to reduce the size of the initial powder particles, because the drag forces from the plume will accelerate the smaller diameter, lower mass particles more quickly. However, small diameter powder particles can present a challenge. As the diameter decreases, particle mass decreases faster than the attractive potential between the particles. As a result, the smaller powder particles, which should give the fastest droplet speeds, instead agglomerate together, making it impossible to achieve the high acceleration of individual particles in their natural state. Fortunately, the small powder particles can be suspended in a solvent which contains chemicals to counteract the interparticle attractions. With proper processing, it is then possible to produce a suspension of dispersed, separated, small powder particles, and that suspension can be directly injected into the plume. After injection into the plume, the suspension fragments, and then the solvent evaporates out of the fragmented droplets, leaving behind individual or small clusters of powder particles that can be melted and accelerated to the desired high speeds. Consequently, performing a coating process using a suspension of yttrium oxide particles has the potential to produce smooth, dense coatings for the etch chamber application. As is typical though, a trade-off exists with this proposed suspension coating process. This process requires more heat than injecting the powder alone, because before the powder can be melted, heat from the plume must also be used to evaporate the solvent. Therefore, a yttrium oxide suspension is best suited to thermal spray applications that can produce particle temperatures significantly above the melting point. In this way, the plume is more likely to have enough heat to evaporate the solvent and yet still have enough time and temperature remaining to melt the powder particles. With this reasoning, we can practically eliminate the suitability of the HVF process because the plume temperatures are not significantly above the melting point of the yttrium oxide powder. Consequently, the most logical choice to produce a yttrium oxide coating via suspension is to use plasma spraying. As previously established, higher velocities are better for making the desired coating structure for the etch chamber application, meaning our high enthalpy plasma spraying is the best choice among the plasma processes. When atmospheric plasma spraying is performed with a suspension, the resulting process is commonly termed suspension plasma spraying, or SPS. Progressive Surface specializes in manufacturing equipment for the SPS process. The 100HE high enthalpy plasma torch can operate continually at power levels up to 105 kilowatts and produce supersonic plasma plume speeds. The liquefator HE is designed to maintain and transport fluids to a torch. These fluids can be acidic or flammable. During the SPS process, the liquefator provides automated flow control while also constantly monitoring the density and pressure of the fluid. This concludes our introduction to the SPS process, specifically that